Hello and welcome back, everybody. Today in geometry, we will be going into section 9.5 and we'll be talking about quadrilaterals and specifically parallelograms and also trapezoids. So now we're going to shift gears from triangles a little bit to, like what happens if you have something that has four sides. So let's go ahead and begin. So these are the topics that we're going to be covering for today then. So as we said, we're going to go ahead and define what is a quadrilateral. Also the stuff that goes along with it, like say sides, vertices, and angles. In addition to that, the quadrilaterals, we are going to talk about the parallelogram and also trapezoid, specific types of quadrilateral. Then afterwards, we're going to look at a few theorems, theorem 914 and also theorem 915. Now, for the last one, the midline theorem, I'm going to go ahead and decide to split that up into a different video because I feel like it's going to be a little bit more smoother in the transition. And it's probably going to, not kill you for... I don't want the video to be like, too long, for example. So anyhow, let's go and begin then. Okay, so first off, we're going to go ahead and define what is a quadrilateral. So here is the symbol that we use to say that something is a quadrilateral, which you can see that there is a box, and then you have the four letters that makes up the quadrilaterals then. So quadrilateral ABCD means the following. First, no 3 points are collinear to each other, and all 4 points are going to be coplanar. So let me just go ahead and kind of draw that picture over here on the side. So for example, here's A, and then let's say here's B, and then here's C, and then here's D. So you'll notice that the four over here, the four sides, they are going to be no 3 points that are going to be collinear. So because if they are, then you're going to form a triangle instead. And if you remember, the points have to be coplanar as well because we don't want it to be one point to be somewhere else in space. So that's the first condition. The second condition is that AB, BC, CD, and DA only intersects at the endpoint. So you can see here for each one of these, they are all the sides are connected only at the endpoints. If they are connected somewhere else, then you're not going to form a quadrilateral because you might have some sort of intersection that forms an X, and that right there definitely doesn't work. So here, A, B, C, D, you can see that's definitely not a quadrilateral then, okay? Next, after that, we have the last condition such that AB union BC, union of CD, and union of DA, that right there is what's going to form the quadrilateral. So that means that the four sides, the union of them, that is going to make up this quadrilateral that we're going to be talking about. And this does not include the interior, so be careful about that. We're just only going to talk about the unions of the sides that makes up that four-sided figure. Okay, next we'll talk about the sides. Those are going to be defined as each of the segments, AB, BC, CD, and DA. The vertices, those are what is known as A, B, C, and D. So those 4 points that makes up the quadrilateral, those are what is known as vertices. And finally, we have four angles inside the quadrilateral. We have DAB, ABC, BCD, and also CDA. Or if you want, you can just call them angle A, angle B, angle C, or angle D, assuming that there's no other, I guess things that are kind of obstructing what are the angles. So next, let's look at the specific types of quadrilateral. So there is something called a convex. If you remember back from, I guess it was like a long time ago, chapter 3. We can say that a quadrilateral is convex if the following is true. Now, first, before we go ahead and define this, let me go ahead and draw the difference between the two then. So back in chapter 3, we said that if you have a set that is convex, then that means that if you choose any 2 points inside, the line segment that is formed by those 2 points will be inside the set as well. So for quadrilateral, it's the same idea. So something like this right here would be considered convex because if you notice, if I take 2 points inside, it is still going to be inside a quadrilateral. But if I draw something like, say, this over here, then you can see that if I pick any 2 points that are over here and also over here, as soon as I create that line segment, that is not going to be considered convex then. So the way we defined it without having to deal with like the two lines thing, because that actually makes it more complex, we just say the following then. No two vertices lie on the opposite sides of a line containing the sides. So here's what that means then. Okay, so let's look at the first quadrilateral over here. So you'll notice that if I create that line that contains a side right there, you can see the other two vertices, they are going to be on the same side over here and over here. If I go ahead and create, let's say, the line that contains this side over here, you'll see that the other two vertices are on the same side. So that's what it means then. But whereas if I go to the other one over here, you can see now, if I create a line that goes through that side over here, you'll notice that these 2 points are on opposite sides. So that is the violation of that statement right there. So you can see what's the difference between the two. Okay. All right, now that we have that out of the way, let's go ahead and define a few more things, and then afterwards we can go ahead and see what's so special about all of these. So the next one is that two sides of a quadrilateral are considered opposite if they do not intersect each other. So once again, let's go ahead and draw, like say, a quadrilateral right here. So here's A, B, C, and D. And so in this case, we can say that AB and CD are opposite sides. Okay, because you can see how they don't intersect each other. Similarly, we can say that AD and let's see, BC are also opposite sides then, because they don't intersect each other as well. So that's going to be the illustration for it. And then for the last part of it, two angles of a quadrilaterals are considered opposites if they do not share a common, they do not share a side that's in common. So here we can say that angle D, and let me just go ahead and use a better pen. Angle D right here and angle B right here, they are going to be opposite angles. So let's see, angle D and angle B are opposite angles because notice they don't share a side in this case, right? They're going to be on the opposite of each other, okay? Then we also have angle A and also angle C are opposite angles then, okay? All right, so now let's go ahead and delve into a little bit more specifically the different types of quadrilaterals that you're going to run into. So the first one that we're going to talk about is something called a parallelogram. Now we're going to go ahead and define it as a formal definition, so then that way we can kind of work around it. So here, for a parallelogram, it is defined as the following. We say that ABCD, the quadrilateral, is a parallelogram, and the way that we denote a parallelogram is very similar to that of a quadrilateral. But you can see that over here, you can see the shape of it. It's actually going to be the shape of a parallelogram, whereas if you remember, for a quadrilateral, we use a square. So that's how you tell the difference between the two. Nonetheless, we say that ABCD is a parallelogram if the following is true. Then this is by definition. Both pairs of opposite sides are parallel to each other. So as a restate, as you can see in the picture on the right-hand side, there we have an example of a parallelogram. And the conclusion is that by definition, ABCD is a parallelogram, implies that AB, the side right there, would then be parallel to DC, the side over there. And in addition, we can also say that AD, the side right there, is going to be parallel to BC, the side then. So that's what we have to work with. Now, that is not to say that parallelogram, we can just go ahead and conclude right there, because if you look at the parallelogram, the shape of it, and also the angles of it, there are definitely a lot of things that we can extract. For example, you'll notice that if we kind of like, just draw it in a picture, and we can definitely prove these in the future, very near future, that AD right here, that length looks like it's going to be congruent to BC right here. Then in addition to that, we can also see that AB is also going to be congruent to CD over there. So that's one thing you can probably extract from it. What else is there? Well, how about the opposite angles that we were talking about? Angle A over here definitely looks like it's congruent to angle C over here, right? In addition to that, angle D over here is going to be congruent to angle B right there. And here is another one that might be of interest also. What if I drew their diagonals? Okay, so what if I drew the diagonals of AC and also DB? So here, let me see if I can sneak that in there. Okay, so here's the diagonal, and then here's the other diagonal. And you'll probably notice that by inspection, you'll see that these two guys looks like they're going to be congruent to each other, and these two guys look like they're going to be congruent to each other. So in a parallelogram, there are a lot of unique things. In this case, it looks like the and the diagonals are perpendicular, sorry, not perpendicular, but just bisect each other, the opposite sides are congruent. Both pairs of opposite sides are congruent. Also, both pairs of opposite angles are congruent, and so on and so on and so on. So that's what this section is about. So here is what we're going to talk about next then, okay? So we'll just kind of, find different ways that you can, different information that you can extract from knowing that you have a parallelogram. So again, by definition, we said that if you have a parallelogram, then the two sides, both pairs of opposite sides are going to be parallel to each other. That's definition. That's, given. Now, what I extracted earlier, those are going to be theorems, and those are theorems that you're actually going to be proving, and they're not too bad. We'll do one of them together. The first one I showed was that, hey, if you have a parallelogram, then it looks like both pairs of the opposite sides are congruent to each other. Going back to the picture over here, you can see that AB definitely looks like it's congruent to CD. And then, in addition to that, AD is going to be congruent to BC. So that is the first one. If you have a parallelogram by inspection for the time being, which again you're going to prove, then both pairs of opposite angles are going to be congruent to each other. If you have a parallelogram, then let's see, one pair of the opposite sides are parallel and going to be congruent. So that is to say, going back to my picture over here, that one says that here, if you have a parallelogram, AD is going to be congruent to BC over here. And then in addition to that, they are going to be parallel to each other. Well, half of it definitely is true because by definition of parallelogram, the other half, you're just going to have to prove that. And then finally, for the last one over here, is that if you have a parallelogram, then we said the diagonals are going to bisect each other. So all of these guys are stuff that I technically haven't proved yet because I actually want you to prove them for yourself. Now, these are not theorems that are in the books, but the thing is, these are basically things that you can extract from a parallelogram. It's going to be things that are going to be useful. So we want them to be in our arsenal instead of like something like a theorem without a name. So let's do this then. Let's go ahead and say the first one, we'll call it, theorem apple. And then the second one, we'll go ahead call it theorem banana. Next one, we'll call it theorem citrus. And the last one, we'll go ahead and name it theorem Dave because I can't think of a fruit that starts with D. So those are going to be theorems that we're going to have for the section. Now, just to show you an example, I'm going to go ahead and prove theorem apple over here. Okay, so in the first one, it says prove the following. Remember, theorem apple, according to this, says that if you have a parallelogram, then both sides of the opposite sides are going to be congruent to each other. So here, let me just go ahead and write that as a restate. Given that you have a parallelogram ABCD, I want to prove that AB is congruent to CD or equal to, and then BC is equal to AD. Now here is kind of like a new symbol that we're going to be using. You can see that we have these little arrows right there. That's to indicate the two sides are going to be parallel to each other. So over here, just like this, AB is going to be parallel to DC according to the symbols. Just as AD is parallel to BC, just according to the symbol. But nonetheless, there you go. I want to go ahead and prove what we have, knowing that we have a parallelogram. Okay. So by definition, we definitely know that the two opposite sides are going to be parallel to each other. Looks like what we're going to do is the following. Well, usually if we want to prove that two sides are going to be equal to each other or congruent to each other, we go back to our same route, which is basically to create some sort of triangles to show congruency for. So maybe what I can do is create DB over here. Okay, so we're going to go ahead and introduce DB. Okay, and that right there is going to be the diagonal. Now, looking at those two triangles, if I can show congruency between them, then we're pretty much good to go. And I definitely do see something because look, remember how we said AD is going to be parallel to BC? Well, then that means that this angle ADB is going to be congruent to this angle DBC. Okay, so we can say that AD is going to be, oh, sorry, not AD, the line. Let me go ahead and erase that a little bit. Okay, we can say that angle ADB is going to be congruent to angle CBD by parallel implies that alternate interior angles are congruent to each other. Well, going by that same model, we can go ahead and say that, hey, since AB is parallel to DC, then that means that this angle right here is going to be congruent to this angle right here. And as soon as you draw those two right there, I think you can probably see why those two triangles are going to be congruent to each other. And the reason is, well, probably ASA in this case. So let me kind of go ahead and sneak that in. So angle ABD is going to be congruent to angle CDB by also PAI. And we want to sneak in the one in between. DB is equal to DB by reflexive. Okay, so according to these, then we can say now by by ASA, triangle ABD would then be congruent to triangle CDB. And then by corresponding parts, okay, so by CPCTC, we can go ahead and conclude what we want, which is supposed to be AD is congruent to BC, and also nailing two birds with one stone, AB is going to be congruent to CD then. Okay, so there's your quick proof of theorem Apple, which is over here. So what I need you to do is basically prove the other two, the other three actually, banana, citrus, and Dave, and that's probably going to be for the homework part. Okay, the way you're going to prove it, same thing, using congruent triangles. The reason why these are useful is, well, you can actually go backwards, right? If you think about the converse of them, it sounds like they definitely are true as well. That is to say, for the following, we can then use these to show that you have a parallelogram. So here, this is going to be the 5 ways you can show that you have a parallelogram. The first one is by definition. If you know that both pairs of opposite sides are parallel, then you have a parallelogram. The converse of apple is if you know that both pairs of opposite sides are congruent, then you have a parallelogram. And then converse of banana, if both pairs of opposite angles are congruent, then you have a parallelogram. And then for these two, let's see, if one pair of opposite side are congruent and parallel, then you have a parallelogram. And then the last one, the converse of Dave, if you have the diagonals that are going to bisect each other, then you also have a parallelogram. So again, these are the converses of the theorems that we have up here, which is something that, again, I want you to actually try to prove, because these are the ways to go backward to show that you have a parallelogram. So just like before, what we're going to do is we're going to go ahead and do a quick one over here to prove the converse of apple, basically the converse of the theorem that we just did. That is to say, if we are given that we have a quadrilateral, AB is equal to CD, then we also have BC is equal to AD. I want to conclude that the quadrilateral is going to be a parallelogram. And in terms of what is it that I need to show? Well, the need to show is that by definition, I need to show that the opposite sides are going to be parallel. So that is to say, AB is going to be parallel to DC, and also AD is parallel to BC. Well, the proof of this, well, it's probably the same idea. Maybe what we can do is introduce that perpendicular. No, it's not perpendicular. We can introduce that diagonal just like last time. Okay. So here, let me just go ahead and write that out. So introduce DB just like last time then. Okay. And if you notice, then we can say that these two triangles are definitely going to be congruent to each other by SSS. So by SSS, triangle ABD is going to be congruent to triangle CDB. Okay. And then now the question is, well, how do you lead into parallel? Because remember, I want to show that this side right here is parallel to this side. That's the question mark. And also this side right here is going to be parallel to this side over here. Well, the way that we showed parallel from the last few sections is that we talk about their alternate interior angles or corresponding angles. And I definitely do see some there, because by corresponding parts, we can say that this angle is going to be congruent to this angle. So by CPCTC, okay, we can say that angle ADB is going to be congruent to angle CBD, okay? And then now from there, we can say by AIP, right? Alternate interior implies that the sides are going to be parallel. AD is going to be parallel to BC. Okay, so there you go. It's very, very similar to the one that we just proved earlier. And similarly, now we can say that by CPCTC again, angle ABD is going to be congruent to angle CDB. Okay, so now we're going to be talking about these two angles right here are going to be congruent to each other by CPCTC. And from there, you can see that they are also alternate interior angles, but to the sides of AB and also DC. So now we can say by AIP, AB is going to be parallel to DC then. All right, so there you go. Thank you so much for watching. I will see you guys next time then. Have a good one. Bye-bye.